So, is my presentation visible?
Yes, sir.
Okay, okay. Thank you. So, good evening, guys. Welcome again to this GATE mentorship session. I think this week will be our last class for this semester. So, how was your guys' preparation for the GATE exam? Hope you guys are doing well. So, okay, I hope you guys are doing well. So the topic that we are going to cover today is about phase diagrams, the problem related to phase diagrams. We will work on some problems based on iron carbon diagram, and also we will look at uh, some problems based on lever rule. So of course this um, lever rule means it applies to both phase diagrams and iron carbon diagrams. So we will see that. And then we will also see some other problems also, such as equilibrium problems. So, yeah, now let us begin. Okay. So, does anyone remember the summary of previous class?
Sir,
What we saw? Yes. Yes. Tell me.
sir, lever rule was covered in previous classes, sir. So we can skip that if you want to.
No, no. Last class we just saw the basic, the formula only. Today we will only see problems. Like we won't go much for the theory and all.
We did one problem regarding lever rule, sir.
Okay, sir.
Yeah. We'll avoid that. I mean, there is some other problems. So I think you can do that.
Okay.
We'll see. Yeah. So does anybody remember what some like what we saw in the previous classes? I mean, last class.
Introduction to allies and Gibbs phase rule.
Yeah, we saw what allies were. Then we saw what Gibbs phase rule was. Then, what else did we see? Hmm.
Triple point. Triple point.
Yeah, the triple point was part of Gibbs phase rule.
Yes,
Mm,
yes, sir. Gives pleasure.
Yeah. Then I think we saw about how to read phase
Different kind of
diagrams.
zone of like yes.
Yeah. In simple words, to say that how to read phase diagrams. So this is kind of what we saw last week, and then we worked on a lever rule problem, right? So lever rule and atomic composition formulae. So this is what we saw, kind of what we saw last week. So now we will see about some problems in phase diagrams, then the lever rule and alloy composition based problems, and again just a summary means like I'll just we can see what possible questions, one more questions can come from the iron carbon diagram. Okay, so first these are the eutectic and eutectoid systems. So we have to we can expect one possible question from this thing. So if any system is eutectic, right? So it is a liquid, okay, that finally turning into two solids, okay, alpha phase and beta phase. This is eutectic. So we have to remember that. Sorry, this is arrow mark. So then eutectoid system. Eutectoid system means one phase, okay, that is the gamma phase or some other phase, turning one solid phase turning into two solid phases. That is eutectoid. Okay, so gamma turning into sorry sorry. So sorry. Yeah, eutectoid means it is gamma turning to alpha plus beta. That is one solid phase turning into two solid phases. Okay. Tectic means liquid turning into two solid phases. Okay. So we have to remember this. This could possibly be asked as either a match the following or some other question. Uh, then there is peritectic phase. Peritectic phase, does anyone know what it is? Like, what will be the possible answer? Okay. Peritectic phases, we have one solid phase.
Exactly like
Yes. Okay.
available at the 0.8% of the carbon.
Okay. That is
No, no, no.
one
That
solid.
is clear light, sir. No, no.
Oh, yeah, yeah, yeah. Perlite is there. So we have alpha plus liquid that turns into one solid. Okay. So this is peritectic. You have to remember. And then finally, peritectoid is sorry. This is alpha one solid plus one liquid. Here, both are solid phases. Alpha plus gamma turning into beta. Okay. So these are the various binary phase systems. Beyond this, there are some more. There is syntactic and monotectic also. So for syntactic, it is two liquids turning into one solid phase. Okay, syntactic means two liquids. Then monotectic. Monotectic means just one liquid turning into one solid phase and another liquid phase. So these are the various phase diagram reactions. Okay, so this can possibly be asked in a match the following. Then now we're going to see about ferrous alloys. So yeah, these are the advantages and disadvantages of ferrous alloys. So they are easy, inexpensive, meaning they are very cheap. They abundant supply. So you have a lot of iron ore in this earth. So we have no problem at all. That's why it is available very cheap, and lot of research is done on this. And many applications are there due to wide range of material properties. So if we add a different composition of carbon, you will have different material properties. That is why a lot of research is happening here, and not just carbon. If you add other elements also, such as chromium and nickel, you will be getting a more refined and better material than crude iron ore. So that's why a lot of research is conducted on this particular ferrous alloys. But the limitations are, yeah, they are very high density and relatively low electrical conductivity. That is, it's electrically conductive, but not as good as some other materials such as copper and aluminum. So yeah, they have a lower electrical conductivity compared to them. Also poor corrosion resistance. So we might have noticed that any iron compound quickly turns into iron oxide, which is also known as rust. So that is also there. Um, then coming to the different types of steels that are there. Okay, so if we classify steels, there are two types. We have low alloy steel and high alloy steel. So under low alloy steel, we have low carbon, medium carbon, and high carbon steel. And under high alloy steel, we have stainless steel and tool steel. Okay, so uh, what we have, this can be a possible question. So if low alloy steel means it must be less than 10 percentage weight of carbon. So only then can be considered as a low alloy steel. Then sorry, 10 weight percentage of alloy. So that we should see. but high alloy means greater than 11 weight percentage of alloy. So that is the high alloy steel. And under low alloy, we have if the carbon percentage is between is lesser than 0.25 weight percentage, it is called low carbon. 0.25 to zero point 0.6 means medium carbon, and zero point 0.6 to 1.4 percentage means it is a high carbon. At the same time, if you are taking high alloy means if you are adding any alloy greater than 10 percentage, we will be having high alloy steel. So primarily it is we have this stainless steel. So stainless steel is also known as chrome nickel steel. So we have chromium, nickel, and iron. So I think sometimes here it is greater than 11%. Usually chromium here will be 18%, and nickel will be 8%. The rest will be iron. So this is stainless steel, and then there are various types of tool steels. So tool steels come under high alloy steel. So we can expect a possible one mark question from this. Okay, moving on. So this is the iron carbon phase diagram, which we already know. So I'm not going to go into much of the details of this particular phase diagram. We will try to directly jump into the problems. But before that, I will just give some pointers which can possibly help you with the one marks. So if you take, do anyone know the different regions such as eutectoid and eutectic region in this phase diagram? Uh,
Yes, sir.
yeah, can you tell me?
At four at 4.3 at 4.3% of carbon,
Yes, 4 point.
11 30 degrees centigrade.
Huh.
11 that is
That is a tick point.
So this is the eutectic point, now. Yeah.
uh,
Sir, what is the meaning of peritactic? Meaning,
Uh,
like eutectic means easy melting.
okay, peritectic meaning as such, I don't know, but as far as I know, peritectic is just that reaction. I know that is this thing, right? One phase turning into sorry, two solid phase turning into one solid phase. But I don't know the meaning exactly. Right? Um, Maybe I'll try to look
Sir,
into.
one solid turning into
No, no,
or two
two solids,
solids.
two solid turning into one solid phase. The alpha plus gamma turning to beta phase. Okay. Yeah. Coming to this diagram. No, I'm talking about the various regions. So this is point. Yes, you're right. This is eutectic point. But let's talk about the region. Okay. So first is from 0 to 0.76. Okay. We have the hypoeutectoid region. I have to write this. Okay, I'll put it here. Hypoeutectoid region. Then from 0.76 to 2.14. Okay, this place.
Hypereutectoid region.
Yeah, exactly. Hypereutectoid region. Then from 2.
Then hypoeutectic region.
Yeah, this is hypoeutectic region, and finally all the way to 6.7 we have hypereutectic
Hypereutectic.
region. Right. So these are the different regions that are there in the phase diagram. And another possible question that can be asked is this one. this gamma plus Fe3C, do you know what this is called?
Austenites.
No, no, no. This
Cementite.
this gamma alone is austenite, right? Then alpha alone. Okay, I'll write it here. So ferrite means it is alpha Fe. Austenite is gamma Fe. Then there is delta. Delta ferrite is this one over here in this region. And then this one gamma plus Fe3C is ledeborite. So I think this was asked in the ESE questions, I guess, once. So alpha plus Fe3C is ledeborite, and then there is perlite, um, alternating layers of uh, alpha plus gamma, right? So these are the different, and finally, yes, there is cementite, which is Fe3C. So these are the these are some of the possible 1 marks that can be asked. So let's move on. Again, yeah, it's the same thing. Okay. Now let's see one problem. So we know that only iron carbon, iron carbide, that is cementite, is has a stable phase at only 6.7 percentage and not any value higher than that. So can anyone tell me why? And how to solve this problem?
Because after this brittleness increases, the material bondability.
That is the saturation state
Exactly.
on the saturation of the carbon.
Yes, exactly.
Beyond that, the carbon is like layers, not in
Exactly.
combinedly mixed properly.
So what happens is beyond 6.7 percentage, the carbon gets saturated, right? And doesn't mix properly with iron, forming layers. So though this is the theoretical answer, what I would say is there's a way. There's also a problematic answer to this question, and that is this one, based on the composition. So let us find the percentage of carbon in Fe3C. Okay. So to find the percentage of carbon in Fe3C, what is the formula? So it is nothing but atomic weight of carbon in Fe3C divided by the total weight. So total atomic weight. Total atomic weight of Fe3C. Right? So what is the atomic weight of carbon in Fe3C? So does anyone know the atomic weight of
Well,
carbon? Yeah, 12. So here in Fe3C, we see that there is only one carbon.
12.
Yeah. So there is only one carbon over here in Fe3C. So it's 1 into 12 divided by, what is the total atomic weight of Fe3C? That is atomic weight of carbon plus atomic weight,
180.
yeah, of iron. Okay, so here we have a 12. Here atomic weight of carbon, again 1 into 12, right? Only one carbon atom. But how many iron atoms do we have here? We have 3 iron atoms. So if we uh,
3.
yeah, if we do the calculation, I think our answer will be 0.06667. So if we term in terms of percentage, we get 6.6%, 6.67 percentage, or approximately equal to 6.7 percentage. So this is the theoretical uh, reason why iron carbon, sorry, that iron carbide cementite is stable only up to 6.7 percentage and not anything higher than that. So so I hope this problem is
Sir,
clear.
while lower than that is
Haha.
sir, while lower than that is
Lower than that is
stable. Why?
hmm, lower than that.
Sir, अगर problematic है,
Sorry, I didn't get you. No, no, lower than that is because it is able to properly mix. So it's not yet super saturated. So sorry, just a minute. Mm. So lower than 6.7 percentage means it is not saturated. So there is a proper mixture, and so we are having a proper cementite.
sir, can you tell example?
Yes.
Sir, can you tell another example where this rule is followed?
Another example, as far as I know,
Like here where compound is
uh, other compound, I think it can be used for, it can be extended to other compounds also. But as far as I read, I saw this problem only. Uh, Maybe we can also use it for dual phase alloys, say, okay, aluminum and copper. So I think even for this we can, I think we can do, but I don't know for sure. Maybe I'll check it, and maybe um, if possible, if we meet again, I'll let you know. But as of now, for iron carbon diagram, this particular rule is used, especially when carbon is involved. So yeah, okay. Maybe we shall we go to the next problem. I mean, maybe in the future I'll try to look into this. Okay.
okay, sir.
Okay. So coming to the next problem. So in the given iron carbon diagram, okay, the eutectic reaction occurs as follows. So that is from liquid phase to gamma plus Fe3 phase. So there's two ways. So on heating we get liquid, on cooling we get gamma plus Fe3C. So we have to find the percentage of gamma and percentage of Fe3C in this particular reaction. Okay, not the steel, in this region. Um, so the composition also is given at the 3 points A, B, and C. So since this is not proper in the diagram, I have given it here itself. So the first point A is at 2.14. The second point B is at 4.3, and third is obviously at 6.7%. So with this data, can we be able to determine the value of gamma and Fe3C? And how do we do this? Okay. We'll have.
Sir, is 6%?
Haha.
Is
What?
gamma 52.6%?
Yes, exactly, exactly. And this one, ferrite, cementite, Fe3C.
47.37.
Perfect. Yes. So how did we do this? It is
Lever rule.
river rule only. Okay. So according to the liver rule, if we want to find out the percentage of gamma, right, then what we do is, we will take the point 4 point, that is b minus a divided by the last c minus a, right? And then for percentage of Fe3C, it is c minus b divided by c minus a. Okay. So we'll just substitute the value 4 point, sorry, 4.3 minus 2.14 divided by 6.7 minus 2.14. The answer is 52.6 percentage, or approximately equal to 53 percentage. And percentage Fe3C means it is C value is 6.7 minus 4.3 divided by 6.7 minus 2.14, which is 47.36 percentage, or approximately we can say it is 47 percentage, because this value, rounding off, we can round off if it is greater than 0.5. So since here it is lesser than 0.5, we can maintain this as 47 itself. So this is the value of percentage gamma and percentage Fe3C. So this is a simple problem. This is clear, right? You can go for the next one.
Yes, sir.
Thank you. So next we will see a similar problem, but we will find it very slightly tricky. Okay. So the problem given is, we have an iron carbon diagram like last time. The reaction occurs at delta plus liquid turning to austenite. So where is this exactly? So if we look at the diagram,
Pentatic reaction. Mm.
perfect.
1493.
Yeah, exactly, exactly. So that is part of the question. Very nice. So the type of reaction that is occurring over here is the peritectic reaction, right? And what is the anyone knows the crystal structure of carbon at this particular region? Sorry, iron.
In gamma, it is FCC. In
Uh,
gamma, it is FCC.
yeah, yeah. In
And in
gamma,
delta, it is BCC.
so in gamma it is FCC, and in
Gamma
delta,
FCC, delta
perfect, and in alpha,
BCC.
uh,
अल्फा मैं मतलब कि
sorry,
BCC होता है सर अगेन BCC
Also
huh,
magnetic.
अगेन BCC
exactly, exactly. So in this case, okay, from delta, which is BCC, it is becoming gamma, which is FCC. So we'll be having FCC in this region, and we have to finally, and someone told about magnetic. Yeah. So if we take iron, alpha iron, uh, below 770 degree, it is magnetic, ferromagnetic. So
It is magnetic.
yeah, ferromagnetic or magnetic, both are same. Beyond 770
Both are same.
degrees,
Above that, sir,
yeah, above that it becomes paramagnetic or non-magnetic, we can say. So the magnetic property of iron only extends till 770 degrees centigrade. Okay. Now we will solve the rest of the problem. So in this problem, we have to find the percentage of liquid and percentage of solid in this particular region. So since it is too small, I will again rewrite it here. So at the region of delta, okay, um, and this is at the region of liquid. So at the region of delta, the composition is 0.09. So this is around about here. Sorry. And at the region of liquid, which is over here, the composition of carbon is 0.53, and in the middle, okay, so it is 0.17. So with this, how can we determine the percentage of liquid and percentage of solid? So we can call this again as ABC.
81%, 81.82%.
Excellent. That is liquid or solid?
That is delta, solid.
Exactly. Delta. Perfect. So just excuse me. Just excuse me. Dude, I'm in class. நான் call பண்றேன். Yeah, yeah. Sorry guys. I got a call. Yeah. So percentage liquid is
It's
equal
solid.
to, sorry, we were talking about solid, right? Delta. Delta is C minus B divided by C minus A. The same lever rule. It is 0.53 minus 0.17 divided by 0.53 minus 0.09. So your answer would be 81.283, right? Or
81.82.
8. Okay, very good. Now for the percentage of liquid, it is B minus A divided by C minus A, which is equal to 0.17 minus 0.09 divided by 0.53 minus 0.09. So our final answer would be somewhere around 18.18 percentage. So that's it, right? We found the percentage of delta and percentage of liquid. Okay. So moving on to the next problem. So during the aging of homogenized aluminum and copper alloy, so that is between 1 to 4 percentage weight percentage of copper. So below the GP solvers line, what will be the hardness of the alloy? So this is actually a very different problem. So this is based on uh, this process, aging. So have we discussed aging before? So I think I think we
No, sir.
no, I think
No,
we
sir.
didn't discuss it. Okay.
No, sir.
So I'll just give a very brief discussion. So the process of aging is also known as precipitation, hardening. So
Precipitation hardening.
yeah. So what happens is with temperature, if we maintain, if we age means if we expose a particular uh, material or metal at a particular temperature, there is a change in the structure. That is the alloy that we are adding, right? Here in our case, the 4% of copper alloy that we are adding, what will happen is that will slowly form precipitates throughout the matrix or throughout the aluminum, the parent material, okay, the parent alloy. Sorry, parent, I can't say alloy, parent element. So this is the process of aging, right? And the question is asking, uh, during the aging process, okay, I mean, I'll just simplify the question. Um, what happens to the hardness of the alloy just below the solver's line? Okay, so the answer is pretty simple only. If we look at the aging curve or the aging strengthening curve, right? If we expose alloy that to a binary phase alloy at a particular temperature, initially um, there is just supersaturation. Okay, the precipitates have not yet formed. Okay, just supersaturation has been reached in the liquid phase, and then sorry, yeah, the liquid to solid conversion phase, and then what happens is uh, there is the formation of precipitates. So at this particular point, it is underaged. So you can say at this region, it is underaged. That is the alloy, sorry, the uh, solute material that we are adding, say that is copper, has formed small and underdeveloped precipitates. So they are too small. But then what happens is, as we maintain it at that same temperature for a particular period of time, then what happens is it peaks at a particular period of time where there is optimum size and distribution of the precipitates for strengthening, right? But what happens is, beyond a particular uh, phase, okay, sorry, beyond a particular time at the same temperature, uh, the precipitates begin to coarsen, and then the strength becomes lesser and lesser. So from this uh, hardness and aging diagram, the answer actually is the hardness or the strength of the alloy first increases and then it decreases. So this is what happens to the hardness of the alloy. So this is not a numerical problem, but this is a more or it's actually an MCQ question. So I'm sorry I didn't get the choices. Forgot to get the choice, but the answer will be in terms of wordings. So yeah, this is a pretty simple problem if you know that concept. Yes.
GP solve.
Sorry. GP solvers actually
GP.
it's Gibbs face. Yeah. So that is a
Sorry, aging is a heat treatment process.
yes. It is a heat treatment process. What we are doing is, but the thing is, what we are doing in this heat treatment is that a constant temperature is maintained for a particular period of time.
So this period of time is in hours or days?
Usually in hours. For some materials it's in hours. Very rarely it goes to days, but usually it's in hours. Very rarely, I remember some alloys they said it will go for days. I
Okay.
forgot like which one, but very rare it goes for days. But mostly it is in hours only. But longer hours. It will take I think a minimum at least 6 to 8 hours. So yeah. So this is the process of aging.
Sir, aging
Yes.
aging is the heat treatment process, but for steel.
I mean, not necessarily steel. It can be any alloy. So in our case, we have aluminum and copper alloy. Okay, so you can use it for steel also. Yeah. Okay, we'll move on.
Okay.
Okay, there's just 10 minutes, so we'll just finish the only two more problems. So this is a little complicated problem. Um, shall we? Does anyone know how to solve this particular problem? So we have a two-phase mixture, alpha plus beta, of a AB binary system. So we have two elements, okay, AB, say like aluminum and copper, okay. So we can consider this A as aluminum and B as copper. Just roughly, I'm saying, we have two elements, and the mixture of these two phases, two elements, is giving two phases, alpha and beta. So alpha has some percentage of aluminum and some percentage of copper, or sorry, some percentage of A and some percentage of B, whereas beta has also some percentage of A and some percentage of B. So we have to realize that um, phase here does not necessarily mean liquid or solid. Usually that is called as in material science we call as medium. Okay, whereas phases means even in the solid phase also you will be having different regions. Okay. Oh, sorry, where is it? Yeah. A homogeneous region of a homogeneous region of the same composition of elements. That is, throughout this particular region, you will have a specific percentage of A and a specific percentage of B. So that is typically what we call a phase in metallurgy. And here, phase alpha has equal weight percentage of A and B. So that is given. That is, we can call this alpha plus beta as, we can call it as x. Okay, and now we can say x has 0.5 weight percentage of A and zero point 0.5 weight percentage of B. Okay, so that is what the first data that is given. The second data that is given is phase beta has twice the mole fraction of A as compared to that of B. So let's call this mole fraction as A. Okay, sorry, MA. Okay, so mole fraction of A is mole fraction of A in beta is equal to 2 times the mole fraction of B in the same beta. So this is the second thing that is given. The third thing is two phase mixture has equal amounts of alpha plus beta. Okay, so the two phase mixture again is alpha plus beta equal to x, right, has equal amounts. So I believe it is uh, equal weight percentage of alpha and beta, that is zero point 0.5 of alpha and 0.5 of beta. Okay, so next what else is given? Yeah, for the atomic mass of A, let's call that capital A again, is twice as that of B. Atomic, or we can call AT, atomic of A is twice as that of atomic weight of B, right? So these are the four data that is given. So the thing is, we have to find the mole fraction of A from the resultant two phase mixture, that is mole fraction of A, m of A in x, or we called alpha plus beta. Okay, so the first thing we have to do is, okay, since there's not much time,
Sir, is the answer 68.75%?
60, which value are we talking about? X
Mole
value,
fraction of
this,
A.
no,
Uh,
actually this is a little complicated. Okay, um, the value of the 67 you told is actually the weight percentage of A in alpha and beta. All you have to do is convert that weight
Sir,
percentage of,
आपकी voice cut.
oh sorry, okay, the thing is, what you told was, I think weight percentage, so that we have to convert it to uh, mole fraction. So okay, no problem. Since there is less time, I will explain. Okay, so first you will find the uh, weight of B, weight percentage of B in the beta phase. Okay, so that is mole fraction of B in beta phase times atomic weight of B divided by mole fraction of B into atomic weight of B plus mole fraction of A into atomic weight of A. So this is similar to the atomic composition problem. So here it is just weight composition. So both have the similar formulas. Okay, we already know from the data that MA is equal to uh, 2 MB in beta. So we already know that. That we will substitute over here. So what we will be getting is MB times AB divided by MB times AB, oh sorry, scaps, plus MA times AA. Okay, sorry, MA we converted into 2 times MB and atomic value also we've given, right? So atomic value of A, that is A of A, is equal to 2 times A of B. So this becomes 2 times A of B, right? So now everything is in terms of AB, and this is 2 into 2, which is 4, and 4 plus 1 is 5. So MB times AB divided by, we get here 5 times moles of A, sorry, mole fraction of B into atomic weight of B, and these two get cancelled. 1 by 5, as we know, is 0.20. Okay, so this is weight percentage of B in beta. Okay, write this, weight percentage of B in beta. Next is weight percentage of A in beta, right? Weight percentage of A in beta is simple. It is nothing but 1 by weight percentage of B, that is WB in beta. Okay, which is 1 minus 0.2, which is equal to 0.8, right? Now we found the composition of A and B
0.
in beta. Yeah. So weight composition of A is 0.8, right? And weight percentage of B is, this is in beta, is 0.2. Okay. Now we have to find the composition of alpha plus beta, right? So to find the composition of X, or in what we call as A plus B, X or A plus B, we used the lever rule. So weight percentage of beta in X or in alpha plus beta is equal to, we have X minus 0.5. So sorry, I'll write this. This is weight percentage of A in alpha plus beta minus weight percentage of A in alpha divided by weight percentage of A in beta minus weight percentage of A in alpha. So weight percentage of beta in the alpha plus beta is, we substitute in terms of numbers, it becomes X minus, so this we do not know, so we can take it as small x, minus 0.5, this is 0.8, that is we saw over here, minus 0.5. So these are given in the question. So these both are given in data. So we already know that weight of beta in alpha plus beta is equal composition, which is 0.5, and when we subtract these two, we get 0.3, which is equal to x minus 0.5. Therefore, your final x value will be 0.65, which is the or also known as 65 weight percentage of A. Right? Now, now we have found the weight percentage of A. To find the weight percentage of B, it's 100. Sorry, weight percentage of B in alpha plus beta, it is equal to weight percentage of A, sorry, 100% minus 65 weight percent, which is 35%. Okay. So we have found the weight percentage in terms of uh, A and B, but now let us convert it into mole percentage. To convert to mole percentage, all you have to do is the same formula as we saw before. Weight percentage, sorry, yeah, weight percentage of A into atomic weight of uh, B divided by weight percentage of A into atomic weight of B. Sorry, I think it's A, yeah. Weight percentage of B into atomic uh, weight percentage of B. This is A. So what we get is 0.65 times A divided by 0.65 into 2 times A plus 0.35 into AB. So our final answer in terms of mole percentage will be 0.5 moles of A in X. So this is the final answer where X is alpha plus beta. So yeah, I know this problem is a little complicated. So I think time is also up. So maybe, if possible, we can try to meet next week. But I think this is the last week we'll be meeting. So any doubts, guys? I think we can stop here, right?
No.
Yeah.
Yeah.
No, sir. Thank you, sir.
Thank you so much. So before
Thank
you
you,
go,
sir.
we'll see just one last problem and we can go. Just one last. There's only one more. This is not even a problem at all. Okay, we'll just see this one and then we will finish.
Okay.
So the condition to be satisfied for
Okay.
alpha and beta phase to be in equilibrium is a two component system. Okay, at a constant temperature AB, constant temperature and pressure is. Okay, so the question that is actually asked is the condition to be satisfied for equilibrium. So for equilibrium, does anyone know what is required?
Sir, Gibbs energy of the system should be minimum and mu A alpha equal to मतलब C option C जाएगा.
So option C, right? It's perfect. The answer is perfect. The reason is for a equilibrium, the Gibbs phase energy must be minimum, and then the temperature pressure, and temperature, mechanical and chemical uh, potential. Not temperature, thermal, mechanical and chemical, not potential also, it is energy. Energy must be in equilibrium, right? So the correct answer is option C. This is the explanation. So
Yes, sir.
you can see chemical potential is maintained. So that is here. Chemical potential is maintained across both phases. There is chemical equilibrium, and then Gibbs phase energy should be at an all-time minimum. So this is the Gibbs phase energy, and the most stable is the lowest energy state. So option 3 is the answer. So thank you guys for joining in the class. All the best for your GATE exam. So hopefully we will try to meet sometime. I'll upload this recording and PPT by tonight itself, so you can prepare.
Okay, sir. Thank you, sir.
Thank you,
Thanks a
sir.
lot.
Thank you so much, guys. I'll also try to upload 1 marks and other things, like not from this topic, rather from other topics
Mhm.
such as composites and
Okay. Okay,
electronics,
sir.
semiconductor physics. So those who are writing GATE XE, for them it will be very very useful. XE and
Semiconductor.
MT. Yeah, semiconductor physics, and this thing I will upload as a Word
Hmm.
format. So maybe those who are writing GATE XE and GATE MT, it will be useful for them. So thank you so much, guys. We will meet
Yeah, sir.
sometime.
Thank you,
Yeah.
sir.
Thank you, Avicii. Thank you. Bye bye. All the best.
Thank you, sir.
And
Bye, bye, sir. Bye.
maybe if you want, you can
Thank you,
even
many
call me.
thanks.
Yeah, if you're free, you can call me.
Yes, sir.
Sure. No, maybe if you're free, you can call me tonight or tomorrow night, anytime. We can discuss. You wanted to discuss something, right? Right.
Yes, sir. Yes, sir. Actually, I have some offer letter from foreign university. So regarding this topic, I had some queries. Okay, sir. Right now we have Vidyaman's class. We have to
Oh,
attend.
sure. Sorry. I'm so sorry. It became late. Okay, no problem. You guys attend. You can call me whenever you're free. No
No, no,
problem.
sir. That's fine. That's fine. Okay. So would it be fine that if I could call you today at after 12 or like 12 a.m.?
Fine, Avjit. Yeah, that would be okay. Sure. I'll be ready. Yeah.
Actually, sir, my main focus is University of Glasgow and Edinburgh.
Okay. So yeah, sure. We'll have a discussion on that, Avijit. Sure, no problem for me. Yeah.
Thank you, sir.
Okay,
Thank
Avijit.
you, sir. Many thanks.
All the
Bye.
best. Yeah. Bye bye.
Bye, sir. Bye.